Chapter 10, Section 6, Solving Radical Equations. So we go through all this expression stuff and how to work with numerators and rationalizing things and working with what these radicals really mean, and then we got to exponents. We've done a lot of these tools, right? Well, in algebra usually that's to get to a point where you can solve an equation. So that's where we're going to apply this into equations, and they're going to bring in some new principles or rules or laws that we can use. This first one is this principle of powers, and then we're going to deal with radical equations with two terms in there, so they have an addition of two radicals, and we'll do some things to work with that, which is pretty similar to things we've done with absolute values as far as strategy. But this principle of powers, it says a radical equation is an equation in which the variable appears in a radicand. Okay, so it's underneath the radical symbol, or I could also say that the exponent of the variable is a fraction, okay, which creates radicals. To solve such equations, we need a new principle. Suppose that A equals B is true. If we square both sides, we get another true equation of a squared equals b squared. This can be generalized. In other words, they don't go through a lot on the proof for this thing, and because there also are some issues to doing this when we get into higher levels of mathematics. When you do these kinds of things, sometimes you can create a false solution or miss real solutions. So, but for this lesson in this chapter, we're going to use this, and that's what this next paragraph talks about, is that the principle of powers is an if-then statement. Usually when we're dealing with principles or laws that we have, it works both ways. So like the addition principle of equation means that I can add the same thing to both sides of the equation, you end up with an equivalent equation. Or I can subtract things. I can go the other way and still end up with equivalent equations, or get back to the original. And this kind of addresses this, that this is not always true. It is not a if-then, well, I lost the term for that, is that it goes both ways. I can't start with a squared equals b squared and assume then that if I take the square root of both sides, then I'm going to get all the solutions. And that's what they're talking about here, is that it's not necessarily true. For example, if we have x equals 3, then x squared equals 9 is true. But the statement, if I started with x squared equals 9, then x equals 3 is not true, because x also has a solution of negative 3. It has two solutions. So based on that, try and go the wrong way with this, we actually lose one of our solutions to this equation. But when we deal with this, when n is even, or that exponent that we're talking about, every solution a equals a solution, but not every x sub n equals a sub n will end up being x equals n. And we raise both sides of an equation to an even exponent. It is essential that we check the answer in the original equation. In other words, the caution is that we could create a false solution, so we have to be careful. Let's look at example 1 here. It says solve the square root of x minus 3 equals 4. Well, the first thing is to isolate the radical, or in other words, solve for the radical, or the square root of x in this case. So when we go here, we'd add 3 to both sides, and we get a square root of x equals 7. Well, using this principle of powers here, I want to get x, so I can square the square root of x, and I have to square the other side, and we get x equals 49. And then we need to check in the original. And I'd say, well, is the square root of 49 minus 3 equal to 4? Yeah, and it does check. In this case, let's look at this, because this is important, very important really, and something to note. This example, we solve the square root of x plus 5 equals 3. Well, you solve for the radical and you get square root of x equals negative 2. This equation has no solution because the principal square root of a number is never negative. We continue as in example 1 for comparison. Well, let's square both sides, and I end up with x equals 4. Well, if I put 4 in for x here, I get the square root of 4 is 2, and then 2 plus that is not 7. So we have an issue with this solution. It has caused a false solution in a sense. So when this happens, when we check, and usually we just check to see if we got the right answer. Well, we should always do this, is that we might think, hey, this worked, I did my math right. I followed that thing that they just showed us in a box, right? And I end up with this, looks good, right? Well, we need to check these because it may not be true. This is probably easier to see, but when they get more complex, it'd be very easy to miss that checks portion. So you'd end up saying you have a solution when it's not true. So here's the strategy. To solve an equation with a radical term, one is to isolate the radical term on one side of the equation. 2, use the principle of powers and solve the resulting equation. In other words, let's get rid of those radicals, okay? Check every possible solution. Check every possible solution. Number 3, they ought to list like 3 times because it's very easy to miss that. Well, let's look at example 3. We got x equals the square root of x plus 7 plus 5, okay? So we isolate the radical, which gives us the opportunity then to square this and actually get rid of the radical. Remember, they have to square both sides even if there's more than one term here, so we have to square this binomial, which is hopefully be pretty easy. Is first term squared, last term squared, and then this term times that doubled, right? 10x, okay? And then we end up with this trinomial equal to this binomial. Well, to get solutions to quadratics or things with powers greater than 1, for this we are going to have to set it equal to 0 and then see if we can factor this to find out possible solutions. Well, they do that. They add a negative x to both sides and a negative 7, and they get x squared minus 11x plus 18 equals 0. Now we use that product of 0 stuff to try to find a solution. Well, I need to factor. I have to have things multiplied together, because the only way you can get a multiplication equal to 0 is one of these has to be 0 or both of them have to be 0. So we use 0 products. We factor this using antifoil. We get x minus 9 times the quantity x minus 2 equals 0. So x could be 9, which would make this 0, or 2, which would make this 0. These are 2 possible solutions. Let's check it. So for the first one here, we're going to check for 9. 9 equals the square root of 9 plus 7 and plus 5. Well, this is 16, right? The square root of 16 is 4. 4 plus 5 is 9. This one's true. So 9 is a solution. If we check for 2, we end up with 2 equals the square root of 2 plus 7. And then that's plus 5. Well, this is 9, so the square root of 9 is 3 plus 5 is it. So 2 does not work in this case. So we only have one solution that makes this true after we find out when we check. Now here they're using a fractional exponent, but if I used again a radical for this, this would be the cube root of 2x plus 1 and then plus 5. Well, if I have it in radical form, I can think about how do I get rid of this fractional exponent is a radical. This fractional exponents are radicals, and the index is the denominator of the fraction. So that's what we usually want to get rid of. So I can do this still all in exponential form. So I isolate the part that has a fractional exponent or a radical, really. And I add a -5 to both sides, and I get this isolated in a sense. Well, now I want this, preferably this, to go to be a non-fractional exponent. And I can take this, use power of powers, which would force or allow me to take a number times 1/3. Well, what number times 1/3 gives me 1? And that's the inverse of 1/3, or 3/1, which is that reciprocal, right? So we have this reciprocal effect, and I end up with this going to 1. In other words, there's no radical here anymore. Again, I don't have a fractional exponent, and I have to cube both sides, so I get this. So I end up with 2x plus 1 equals a -125. Negatives make a difference. Don't forget the negatives. I hear a lot of students say, well, I just get the negatives wrong. Negatives are a big deal. Be careful. Okay. So I add a -1 to both sides to get 2x equals a -126 and x equals -63. Because both sides were raised to an odd power, the check is not essential other than checking to see if you got the right answer, but it is wise, however, to confirm, right? But when we have odd exponents, that issue of creating a false solution goes away. And it's mostly because of the sign issue. Odd things they continue to represent their signs well. So it's kind of nice when there's odd powers to work with. It actually makes less work in the check process for sure. Now, probably the more complicated thing of this, and definitely the more complicated thing of this lesson, is the equations with two radical terms. Now we're going to deal with binomials squared and those kinds of things again. But the strategy is pretty much the same here. It says isolate one of the radical terms, because we're going to have two of them. We're going to decide, and this is really strategy. You're going to, as you do a few of these problems, you're going to find that hopefully not one way is the way you like to do it because you just had it work that way one time. Think about what happens with these things so you can probably find a strategy to isolate the one that'll make less work. So think about that when you're working on the problems. And then when we have one isolated radical, we can use the principle of powers. If a radical remains, perform steps 1 and 2 again. So we're going to do a repeat in here if we don't get rid of all the radicals. So let's look at that. And then when the radicals are all gone or fractional exponents are gone, we just solve for the variable and find out possible solutions. And then if we have any even power issues, we need to definitely check and find out if we ended up with a false solution or not, and take the one that works. Well, let's look at this equation. The square root of 2x minus 5 equals 1 plus the square root of x minus 3. Well, it is already isolated for us, or this one is, and there's a good strategy. Hey, this part's already done. Don't do more work than you need to, and just use this. And then it's isolated, so let's square it. Since it's square root, or this is half power, what do I take times a half power is 2. To make it 1, so I have to do that times both sides. This little note here is very useful. This is similar to squaring a binomial, and if you can remember these shortcuts, boy, it's going to save you a lot of work. You know, and they say here, you know, study this carefully. This is a review of squared binomials. Is that, well, this ends up being 2x minus 5. Well, to square a binomial, the shortcut is the first term squared, which is 1 squared is 1. The last term is this squared right here, which ends up to be x minus 3. And the middle term is this times this and doubled. So 1 times the square root of x minus 3 times 2. and you get this. Well, this radical goes away. We have some things that we can add, and we end up with a lot of stuff. And basically they're skipping a lot of steps here because it does take a lot of steps to solve these. But they've added basically this 1 and a -3 is -2. They added 2 to both sides. That's how they got this -5 to go to 3. And then they also have an x here, so they took a -x times, added a -x to both sides, and you get 2x goes to x. So now I have x minus 3 equals 2 square roots of x minus 3. Now they don't isolate really. They got this too, but you know, squaring things that are factors or parts of a multiplication it's not very hard to do. So this is probably good strategy. Say just square both sides. This is that squared binomial again. First term squared, last term squared. -3x doubled is a -6x. This one is 2 times the quantity x minus 3. 4 times, I think I said 2. Remember, it's 2 squared, and then x minus 3 is the square root of x minus 3 squared. Okay? So we still have a power of 2 here. Looks like a quadratic. We're going to need to set the equation equal to 0 and factor to find solutions. Now we're dealing with we squared things when we were going through this, or took it to an even exponent. Make sure that you check both of these things to find out which one is your true solution, or solution, which values for x will make this equation true. Very common area when they talk about one of the things I like about this book series is they do point out real common errors, and I do as a teacher. I see a lot of these. Common error for solving equations like this is to think that when you square something like this right here, 1 plus is you can just take this squared and this squared. But a plus b, the quantity squared, does not equal a squared plus b squared. We end up with that. It's going to be a squared as a first term, b squared as the last term. Then it's going to be 2ab as a middle term. Okay. Well, let's look at this one here. F of x, we've got a function format here. It says find all values of our x for which f of x is equal to 2. Now, we must have f of x equals to 2, or what we're going to do is end up with this equation, right? They're talking about the result is 2. They didn't tell us what the x is to put in here, but it creates this equation where I have these two, this difference of radicals here is equal to 2. Well, they isolate one of the radicals, so it'd be somewhat tempting to go in here and say, well, I could take maybe difference of squares on times that. It'd be kind of interesting to go through that and say, well, I could take this whole thing, but I don't think you're going to solve any or make it any easier, because those radicals are just going to go to the other side and not necessarily give you a simpler one. So the strategy is to isolate one of these radicals. In this case, they take x plus 5. So they added a positive square root of x minus 7 to both sides, and they end up with this new equivalent equation. Well, we can square both sides now. So this ends up to be x plus 5. This is squared binomial, first term squared, last term squared, 2 times these multiplied together. There's that middle term. They simplify what they can. And again, we have a radical still, so isolate it. They add 3 to both sides. You get 8 equals 4 times the radical square root of x minus 7. Now in this case they do take this factor out and they take 1/4 times both sides and they get, and I would definitely do that. In fact, you could have done it in that prior example too, and probably in the same amount of steps found out your solution. Well, they got this isolated so we can square both sides and we end up with 4 equals x minus 7 or 11 equals x. And we check this. So f of 11, so we're going to check, go back to the original function, fill in 11 for the x, and find out if you end up with something that's true. And we wanted to find out if it's equal to 2. So if I put x in for 11, I end up with 2. And that's exactly what they said f of x should equal. So that is a solution. And that's the end of that section.